Welcome, everyone. My name's... Oh, I get Thank you. My name is Andrew Richards. I'm the CEO of CodePlay, which is now an Intel company. And what we do is we focus on building out the open ecosystem for software, high-performance software, accelerated computing software. But I'm going to start with a little story, long before my time at Intel. But this is about unlocking the next 35 years of software for HPC and AI. So the reason 35 years, about 35 years ago, the ASCII-read supercomputer was created. And it was the first supercomputer based on normal microprocessors that you could buy in your PC. Before that point, people tended to make supercomputers out of very expensive custom systems that were much more powerful than you could get into your normal PC. But the challenge, therefore, for developers is how do you develop software for a supercomputer that's totally different from the PC that's in front of you? And that's going to be some of the subject of what it's like today. How do we develop software that can then run on all of these new supercomputers? Because, of course, in the modern world, it's all now about accelerated computing. And that's what we're going to talk about. There's heterogeneous systems where you have CPUs and other forms of accelerator on the system. You might have a GPU, something that I care about, because I used to be a video game developer. That's why CodePlay's got the name CodePlay. We started in video games, and people started using GPUs for other things. But there's also a range of other accelerators that might be a much better fit for certain supercomputing applications. So the challenge for people who are innovating today is that you often have to compromise on openness in order to be able to get the maximum performance out of your system. You have to start saying, well, I'm going to get the maximum performance out of a system with this kind of accelerator, but I'm now going to have to use more closed programming models or programming models that are specific to one kind of processor. And that makes it much harder for developers to be able to develop software for a big system. It maybe compromises your principles. I know a lot of developers really care about openness. Openness is part of what they do. It makes it harder for you to integrate different technologies together. You know, it's much easier to integrate different technologies when they're open because they're standards. Standards fit together. It's much harder to do that with closed systems. You also lose the freedom to choose the best processor for your workload. If you've had to write your code for a particular kind of system, and then suddenly, a new kind of system which is maybe a better fit from a hardware point of view for your software, how do you move it across? It becomes very difficult. So you lose that freedom. And it also makes it much harder for innovators to bring new kinds of processor to the market, because then suddenly they have to get everyone to rewrite their software in a completely new way for their new processor. So these are big challenges that we're setting out to solve, and it's something we can't solve on our own. It's something that we have to solve together as a community. So the vision that we're setting out is an open ecosystem of software for accelerated computing. We have lots of open ecosystems for CPUs. We're putting forward a vision of an open ecosystem of software for accelerating computing, as well as an open ecosystem of accelerator hardware. Open hardware that can accelerate open software, but can be adapted to your workload. And then have everything tested and working together. So it's not just a cool experiment or a cool demo, but actually something that you can use and something that you can rely on because we've tested these things working together. And then we're going to enable users to choose the right technology for the job. So you'll notice every time I talk about a technology, I'm going to talk a lot about SYCL because I was very involved in SYCL, but actually that's not really what it's about. I really like SYCL. Sometimes it's the right solution for the job, and we're going to talk about it. Sometimes it's not. Sometimes you have a Fortran code, you need to be able to use Fortran. Sometimes there's other systems, right? There's industry standards for all of these things, but it means as a developer you can choose the right technology for the job that you've got in hand. And we're also going to make it easy for innovators to bring new ideas to market. And this is another thing that I really care about, because I think it enables all these exciting innovations to happen. So, from my story is, in 2014, I was very involved in the SYCL language for open portability. We'd seen a lot of hardware at CodePlay. We had worked in lots of hardware companies, but we'd also seen some advanced software using C++, for example, and there's some really great things going on in C++ to enable people to achieve performance portability. But we really needed to take that a step further and convert that into an open ecosystem. So it's not just a programming model, it's also libraries, it's also implementations. It's how you plug all of the pieces together. How do you have optimized libraries for individual processors? At Intel, Intel's been putting a huge amount of effort into creating the one API software technology and ecosystem. But we needed to take it a step further. It was open source, but it was an Intel project. We needed to take it a step further and convert it into a truly open, industry-led project where different vendors, different hardware companies, different software developers would come together and create a project that was truly multi-vendor and open. And that's why we decided to start this UXL Foundation, and we got together with a lot of other like-minded companies to create this new open industry process. So the solution, I call it an open software platform. It's based on industry standards. And what that means is software applications above. You have programming models, SYCL that I care about, but other ones. We've got other language interfaces, so you can bring other ones. It's all part of the system. And then optimized libraries. So you can build your application on top of those languages, combined with the optimized libraries, combined with compiler technologies, all the cool stuff's going on. And then underneath, we've got an interface for different kinds of hardware, and we enable people to bring new hardware to that. So there's quite a lot going on here, but I'm going to bring on 4 guests today who are going to talk about all of those individual components and how they're making it work for them. We have achieved huge progress. When I was talking about SYCL many years ago, we'd have maybe one bit of an application or something like that. Huge numbers of applications have been ported across. A lot of people have actually found it's much easier to develop in SYCL or with one API. And a lot of people, when we say CUDA to SYCL, sometimes people use CUDA and SYCL at the same time. Sometimes you use CUDA, HIP, SYCL, or C++, CPU, C++. They use lots of different technologies. Often people actually use things like OpenMP, Fortran things, all plugged together because these technologies work together. So actually, it's possible to maintain software across industry standards and use the features of proprietary programming models when you want to get maximum performance. And if you're a developer saying, well, I've built my application out of components from different sources, there's C++ frameworks and there's languages and things, I don't want to have to port all of the libraries that I've used. A lot of those libraries and frameworks have already been ported, and so they're all ready to go on an open ecosystem. So it's a huge amount of work that's been happening here. And now I'm going to call on my colleague, Rod Burns, who's also at CodePlay, and he's the chair of the UXL Foundation and the steering committee. Come on up, Rod. I'll hand you the little clicky. Press the green button there. Don't press the other one, otherwise you'll laser people.
OK, thanks. Yeah, so great to be here. Thanks, Andrew. So yeah, as Andrew said, I'm the chair for the UXL Foundation Steering Committee. The steering committee makes high-level decisions for the foundation, as you'd imagine. I also work at CodePlay. I've spent quite a few years helping and working with developers to adopt and be successful with with open standards too. So we're talking a bit about how the computing landscape has changed, I would say. And the widespread adoption of, if we'd call accelerators, has really reached across the industry. I don't think there's many verticals that aren't looking at accelerators as a way to get much better performance. And obviously GPUs are leading the way, and you can see that from the top 500 supercomputer lists, but there are certainly other emerging accelerators that are focused on more specific workloads like AI and things like that. So what this really means is that organizations are looking to the industry now to say, we need an open standards, open source based way to write software that can run on any accelerator, regardless of what vendors made that processor. And that's why the UXL Foundation has been formed. So we want to achieve that. So I guess the key thing about this foundation as well is that it's building on a really, really solid base. So we're building on, I guess, the past 5 years plus of engineering effort that's gone into the One API specification and the projects that implement that specification. So these projects are covering all the building blocks that developers need to build the types of applications that can take advantage of the performance that comes from accelerators. So we have a specification, we have projects, and we've set these up under the Linux Foundation so that we have an open governance model, and we've brought together a bunch of, as Andrew says, like-minded organizations that can help us to fulfill that goal. So, our mission is to, as it says there, it's maybe a bit cheesy, but we want to free developers from proprietary software, help them to use open standards so that they don't need to worry about the type of processor that you're using, but they can choose the best one for their workload. So these are the organizations that we have as part of the foundation at the moment. At the steering level, these organizations have a seat on the steering committee, of which I'm the chair, where they're able to help guide and influence the high-level direction of the project and the specification. You can see there's a bit of a cross-section of processor companies bringing really deep hardware expertise, but alongside that we have software companies who have obviously deep expertise in different areas too, in AI and cloud and beyond that. We also have a growing number of contributor members. Similarly, there's quite a good cross-section between companies that are building some slightly unique or novel new accelerator processors that can be used, particularly in AI. But also we have a lot of software companies that are bringing deep expertise in areas from RISC-V through to some other tooling areas and things. So I guess the main message from this for me is we'd like you to join us on this mission, help us to define specification, build these projects out. The best way that we can make this work for everyone is to bring you all together and make sure that the people that are working on the projects and the specification get your feedback and build it to meet everybody's needs. You can check out the website, and you can also use those QR codes to sign up to the mailing list and the Slack where you can find out more information about that. We do have varying levels of memberships. It's quite, I guess, simple 3-level memberships. So you can join at a contributor level for free. So you've got no excuses to avoid doing that. So yeah, please join us.
Thank you, Rod. So I noticed there were quite a few other hardware companies doing different kinds of processors.
Exactly, yeah.
Many of them competitors of Intel. If they want to add something or change something, can they do that as part of the UXL Foundation?
Yeah, so really the main purpose of the governance model is to bring together technical forums through the special interest groups, working groups. It means that anyone can really bring bring their feedback into those, but also make proposals. Those can be discussed like any other standards-based governance model would allow.
And if I'm a software developer and I need a special feature or I want to change something, can I request something, or can I even just change the code myself, just submit a pull request? Is that something I can do?
Yeah, I mean, they're all open source projects, so everyone's welcome to submit pull requests. There's obviously procedures in place for like major proposals and things like that can be discussed by the community, but yeah, anyone can contribute. That's the whole point of open source. The licensing model uses Apache to be as permissive as possible, and really that's what it's all about.
Okay, so that's fantastic. That means I can bring my new hardware. I think I'm going to be talking about that later on because that sounds very interesting. And I can also bring my new software to it, and I can make changes, and I can even join for free. Wow, how exciting!
Yep.
Thank you very much, Rod.
Okay, thanks, Andrew.
So, next I'm going to invite up Kumar from Argonne National Lab. Kumar has been responsible for the software and is going to talk less about the supercomputer, more about the software, because you have supercomputers built with hardware from all sorts of different vendors, some with CPUs, GPUs, different vendors, and that must be an incredibly complicated thing to do.
Yes, Andrew, and Aurora has been in the news, but that is not the only system we support in our facility. We do have other flavors of GPUs from other vendors. But Aurora has been in the news for all the benchmarks, but what I want to talk about here is the open standard programming models we have adopted in porting applications to Aurora so that they can be supported on the other pieces of hardware we have in our facility.
Great.
So one of the things that we do have on Aurora is we adopted the applications that we developed through the early science program for Aurora or the exascale computing project. We made sure that they adopt an open standard programming model. In that, it is either SYCL 2020 or OpenMP. More than half of our applications that are being developed use SYCL, either directly or they use a higher level programming model like Cocos or Raja with SYCL underneath. Almost all of them that use the GPU uses the V standard, open standard. And when it comes to tools or compilers, we use the LLVM infrastructure supported on Aurora. When it comes to the AI space, we've built a software stack with frameworks like TensorFlow or PyTorch. We have optimized them by using one API, and we have scaled them using any of the programming models or any of the software that we use using one CCL. So our software stack, whether it's NVIDIA or the Intel GPUs, for the AI space is very similar. And so it's very easy for our users to run their applications in any of the systems we have. So I'll go through 3 examples, 2 of them from traditional simulation apps as to how they have ported to Aurora and how they can run on other systems. And one of them is in the AI space. So HACK is a code that is developed. It stands for, it's a cosmology code with hydrodynamics. It stands for Hardware Hybrid Accelerated Computing Code, Cosmology Code, sorry. And it has been developed in CUDA or HIP and SYCL 2020. But what I want to point out here is that the SYCL developed code not only runs on Aurora, but it can also run on the NVIDIA GPUs and the AMD GPUs. And you see a bar chart comparing performance, and I didn't add it to show that the Intel GPU, the PVC, does better than the A100 GPU that we have in Polaris or Perlmutter, or the MI250X in Frontier. But the main reason the thing that I want to point out is that the native programming models supported on these platforms, be it CUDA or HIP, the SYCL version runs as fast. And so the development of this SYCL 2020 versions that we support on our platforms were developed through a partnership with you guys at CodePlay. Another example would be an electronic structure code called NWChemX, a chemistry code that supports various methods. And once again, I want to point out that the support for SYCL 2020, they do have native programming models supported on both the NVIDIA GPUs and the AMD GPUs. But the SYCL 2020 version that they run, that's developed for Aurora, runs as fast on NVIDIA GPUs as the native programming model, or the AMD MI250X. Another thing also is this code is run on CPUs too, and they can use the SYCL version to run on those. And finally, an example about our AI software stack. This is running a large inference model. It's called a Smiles Transformer. The software, and this is used for drug screening and designing therapeutics in drugs. And one of the things here is that the software stack is a transformer model, and it runs in inference mode on a PVC tile. And the takeaway here is that you see that it's scaled on the PVCs. We've tested it on 128 PVC GPUs and 256. And the 256 version can screen about 22 of the drug molecules on them, and that 22 billion, I should say. And so that's much faster than what we have seen on Polaris, which is our NVIDIA GPU machine. And what we want to do is, now that we have done with the benchmarks, is to be able to scale it across the entire platform, and we can think that we can solve or run a trillion molecule model on this.
Great, thank you, Kumar. That's really interesting. So these are real scientific applications that you can just run on industry standards, on multiple GPUs, CPUs. And very portable across any platform. Wow. Performance portable. So you say performance portable, but I mean, I'm thinking in my head, is that like, is this magic? Or does somebody have to do some work here? The main work is to support SYCL 2020, and we as a facility will continue to do that on different GPUs, but it gives us the flexibility to have these applications run on any of our platforms currently that we manage, or in the future we buy. Yeah, and how hard has this been? How much of an effort is it to be able to get these applications across?
Not much, because they do develop for Aurora, which supports the SYCL programming model or the OpenMP target programming model. But to have them running on the other platforms, we need SYCL 2020 supported. So that is the thing. That's something the facility provides as part of our support process.
Yeah. So interestingly, if I'm buying a supercomputer, do you just say, I want this all to be industry standards? Is that a request that you make when you ask suppliers?
That is something that the facility has adopted, that we would prefer open standard programming models. One of the points that I made on my first slide, which I failed to point out, is that we aggressively work in these open standard bodies, like OpenMP, like SYCL 2020 with the Kronos, and push any of the performance metrics that we want to achieve performance with these programming models.
Right, okay, that's interesting. So you get involved in organizations.
Correct.
And
you hope to be involved in UXL too.
That would be fantastic to have you involved in UXL. And then you make the demands of, or the requests of what scientists need, developers need to be able to get the performance, to be able to
make it an HPC programming model.
Yeah, the features that they need. Yeah. And it wasn't, because I was talking about SYCL, but it's not just SYCL on your slides, is it? You're using other industry standards like OpenMP.
OpenMP, SPIR-V, LLVM infrastructure, and yes.
So you're using a range of different industry standards, some of which are not part of UXL Foundation. So OpenMP is not part of UXL Foundation, but you're able to use them together because they're industry standards.
Correct.
A great proof point for openness, which is what I'm talking about. Thank you very much. It's been great having you.
Thank you for having me.
OK, so now, for me, is the most tense part of today's talk, because we're going to do a demo. Let's see if the demo works. So Tobias here is a developer, and great to have you here. So I'm going to take you over here, because I promised, remember, I promised at the beginning, that you were going to be able to write supercomputer software on anything from a laptop to a normal PC up to a supercomputer. So take it away.
Thank you.
Nice.
So I want to show an example that hopefully just showed up on the slides. I want to show an example of the software that we have been developing in Karlsruhe and now moving to Munich, or Heilbronn more specifically, as the Ginkgo software package that is meant for sparse linear algebra across GPUs and multi-core CPUs using different programming models. And basically, we started working with Intel and the One API framework, or SYCL, as a more general standard in 2020, and started developing a separate backend that relies on SYCL to be able to run on the latest Intel GPUs. And what I want to show today is basically a pre-built version of an example that we have in our library that was compiled on a completely different server with a completely different GPU, and that is now running live on the built-in GPU, the integrated GPU inside the CPU on this laptop, so we can see what is possible, like using SYCL across different things. And what we need to do first is just set the necessary environment variables, and then we can show. Then we can show our examples, and that example is basically solving a 2D heat equation, like with a finite difference scheme on a small grid, and basically doing that for a few time steps. So first, everything has to be initialized, and then we are running on the integrated GPU, doing our time steps until we've reached our 5 seconds. And in the end, this produces a few frames and turns it into a video, just so we have a nice example that we can show for people to see what is going on. In the end, we see like a small performance overview of what different operations have been executed. So the 2,500 linear solves, like the time steps, and did average like 3 iterations per time step. And now if we want to see the result of this, we can look at the generated video. And this is basically a version of our logo that was kind of scaled and used the right legend. So we can see, so we can just solve the heat equation on this with the source term, which is our name, and the initial guess, which the initial state, which is just the rest of our logo. And this is basically showing how easily we can run something that was compiled on a different system and also was running on a different system now on this integrated GPU. Originally, we were thinking about also showing a bigger example, because we also have an integration into OpenFOAM, which offloads the linear solvers onto the GPU. But this is aimed for a multi-GPU system and double precision. So getting this to work on an integrated GPU with single precision was too much of an effort. So we went with a simpler example we could easily show without taking too much of a risk.
Yep.
Thank you.
Thank you very much. So I'm relieved that it worked. And what's interesting about this is that I think really using GPU-accelerated computing or other kinds of accelerators on low-power devices like this is really quite unexplored, because you can get all sorts of benefits from having this processing that's here, and now you can develop software. And this is a library, isn't it? Ginkgo is a library
exactly.
that uses, that can be brought to all sorts of systems. And one of the reasons I thought it was interesting is because when we were talking about the UXL Foundation before, many of those members are doing things like processors that were going to a car, processors that were going to small embedded devices. So we're really bringing this accelerated computing from everything from very small embedded devices to laptops up to supercomputers, but you can scale that same library between them. So as a developer, I'm a little bit interested in seeing what the code actually looks like, because this is kind of looks like normal C++ to me. It doesn't look particularly special, but you are able to use C++ and all of these templated techniques, which I know have become very popular recently.
Yes, exactly. I think that's also something that can be very powerful, especially because we are building across different data types, different index types. We incorporate mixed precision into these computations and other things that all bring us together to be able to just write this single kernel for a specific type of matrix vector product and have that work across all the different precision formats, all the mixed versions of precisions, and all the different architectures with little requirement to actually do performance tuning on this code. We're mostly filling with parameters like subgroup sizes or work group sizes inside SYCL. But in general, this allows us to work across quite a wide range of devices with the same code base.
So you brought up something there that I find interesting, because people say, oh, well, how can you possibly get the maximum performance across all of these different devices with all these different parameters? But because we're using C++ and templates and things like that, you're still modifying it. You're still changing the subgroup size, the group size for different processors, but it's the same code. We can see there that the subgroup size is a variable, so we can define it according to the hardware.
Yes,
yeah.
Exactly. That's also something that we needed to put in a bit of effort. So initially, we had a CUDA and HIP code, and we used the compatibility tool that was provided in one API to transform this into SYCL code. And then we had to do a bit of fiddling because not everything worked out perfectly in the beginning in 2020. But now it's gotten pretty stable to like transform some CUDA code that we've written into SYCL code and use it across different devices.
Okay, fantastic. So we're not going to do optimization developers out of a job. We're just going to make you more productive, I think is the message that I got out of that.
Yes.
Yeah, that's right. Fantastic. Great to have you. Right. Thanks, Tobias. So I promised that this would be a multi-vendor, multi-hardware standard, and then I promised that we would enable new innovations in hardware. But how? How does somebody go about designing new hardware, bringing their new hardware to the UXL Foundation? Now, one of the things that we've done in the UXL Foundation is we've documented everything very carefully, and we've built it in a way that can run on different hardware systems. So we make it very, very easy to bring your new hardware to the UXL Foundation. Now, there's various ways you can do it. You can do it using OpenCL, for example. You can just go off and do it. You can just choose to do it any way you like, to be honest. But we do have the One API construction kit, which is open source, but provides a whole load of documentation to explain to you how to do it. So I'm not a hardware designer, but I'm going to simplify it as a software developer. What we generally find is we have an application code, we have a CPU, and then we have an accelerator. And that accelerator runs lots of kernels in parallel, or maybe one kernel in parallel across a lot of systems. And it's probably got some special features in it to be able to do things like, AI, matrix multipliers, those kind of things. Those are common. And then you have to be able to move data around the system. So although there may be specifics that are different between different kinds of processor, in fact, what we've done is we've kind of generalized it and shown you where they fit in within the One API and UXL Foundation software stack. So if you are thinking about, oh, I want to bring my hardware to it, how would I do it? Maybe you're looking at it and thinking, well, One API, the way it's done at the moment, SYCL, the way it's done, doesn't quite map to our hardware. This is going to help you work out how to do it. And we've got open governance, so if you do see something that really isn't going to fit your hardware, you can turn up and say, I want to change that. So my next guest is going to talk about that. Bongjun Kim. Unfortunately, you've missed his presentation. He did a fantastic presentation earlier today. I hope you saw it. Yeah, please come up. A really, really interesting presentation earlier today about bringing SYCL and One API and OpenMP as well. I noticed there were some other standards as well, to processing in memory.
Yes.
PIM,
processing in memory.
which I think is a really, really interesting hardware concept. Can you tell us a little bit about it, about what you did?
Yeah, so actually I had a talk this afternoon, so it was about the programming models for the processing in memory. It is about the compute, the reside inside of the memory. And also I also want to talk about more about the processing near memory today. So that's about it. So we want to place the compute near the memory or the inside of the memory. So that's about the processing memory and the PNM.
So that's interesting. It's quite different from anything I've heard of before. So what's the benefits of doing the processing in the memory?
So the benefit, in polynomial architectures, you can easily, experience with the memory bottlenecks because, in these days, such as the LLM, so requires a lot of the memory you should feeding into the compute. So your GPU cores will, experience the underutilizations in the polynomial architectures. So you need, in this case, you need to, use some processing in memory to, alleviate the memory, memory bandwidth problems.
Yeah. So I mean, I think anyone doing HPC is going to have found parts of their application, maybe all of their application, that's very bandwidth bound, that they have all of this floating point processing power, and we don't talk as much about the difficulty of accessing the data in memory. So this processing in memory or processing near memory is really going to be able to help people with that. Yeah. How easy did you find it bringing SYCL to what's really a very interesting and innovative processor design?
Yeah. So actually, it depends on how do we abstract our underlying the low-level SDK to the one API-based software stacks. So, but I can say that it was quite easy because we decided to design the processing in memory and the processing near memory API as aligned with the SYCL the group functions. So it was easy in terms of the design. But I can say that they're a little bit complex in terms of the implementation. But as a user or the programmers, you can easily use our new extensions for the processing in memory and processing near memory.
So that's actually, you brought up something that I was thinking about, because when we designed SYCL, we weren't thinking about processing in memory. So you've extended SYCL with some of the special features of your processor in memory. And then what, are you going to propose that back to the SYCL standard, or you can bring that to the UXL Foundation?
Yeah, so I hope so.
That would be great. Yeah. So I think that this is a really good idea of, it enables people who are thinking about that hardware. You have demonstrated that it is possible to analyze SYCL and one API, see what the issues are. If you need changes, you can bring it. And then are you able to get existing software working? I assume you have to make a few changes to your software. Yeah. But it's like Tobias was saying, it's like small changes.
Yes, small changes. Yeah.
And you're working with other standards as well.
OpenMP?
Yeah, you're working with OpenMP.
Yeah, because we don't want to stick to the one programming models, so we design the directive-based APIs specifically for the OpenMP and OpenACC.
Yeah. Okay, so that's great. So I mean, it's a really good example about how openness means, you can use the right tool for the job. Sometimes you want to use SYCL, sometimes you want to use OpenMP. Those things can work together. That's fantastic. Thank you very much. Thank you very much. It's been great having you. I look forward to hearing more about that hardware in the future. Okay, now, if you want to find out more, this has been quite a high level. If you want to find out more, we're going to be talking quite a lot more about some of the things that we've been doing in the UXL Foundation. Later this week, we've got, I think it's me going to be talking about it at the RISC-V ecosystem. Another open ecosystem. RISC-V is another open ecosystem that we're actively engaged in. So that's another really good example of how we can fit different technologies together. We're going to be talking about ISO C++. I didn't really talk about ISO C++, but of course ISO C++ has things like the parallel STL, which was another really good industry standard way of developing high-performance computing software, and you can make that software work on an accelerator. And like I said, we work together, and that's the great thing about open standards. We should be working together to enable these things. So there will be people talking about that. There will also be people talking about alternative ways of using ISO C++ on different hardware. I think it's a really good example of how we can work together. We're going to have the XBug workshop, where one of my colleagues is actually going to be presenting some of our research in it, and you'll see some other things. And yeah, we've got a workshop on RISC-V for HPC. So, please come and join us. It really is very easy to come and join and be part of this open ecosystem that we are building together. I actually think it's a very exciting time to be involved in high-performance computing and this accelerator ecosystem. We've seen so many innovations, different kinds of hardware. The thought of being able to enable different kinds of hardware, hand it over to software developers, and software developers can just, it's so easy to just download and install the tools to be able to run on your laptop or whatever device it is, get that working in an open ecosystem, and this new performance is going to enable software developers to create new innovations, to solve new scientific problems that I haven't thought of, other people don't know the answer to, but we are enabling people to be able to build these new innovations in hardware and software. And also an invite to Intel Innovation, which is going to be in San Jose in September, where I'm sure we're going to be talking a lot more about all of these technologies. Thank you very much. Okay, that's it. I think we can go off and have a beer or two. Thank you very much.